Now let us take a look at 2.5, where we are asked to solve a system of linear first-order ordinary differential equations. And they say, consider the system of linear ODEs given by y of t equals a times y of t, where t runs between 0 and infinity, and y of 0 is given by y0. And what is special about this compared to what we have known before is that this is not just one differential equation, it is actually a system of differential equations. And what we mean by this, well, if you have a hard time with matrices, then take a look at the matrix video and come back. Or else let's just continue. What we mean by this is that actually, oh, forgot a prime here, that actually we have 4 equations that govern our system. The first equation is y prime 1 of t is given by 8.5 multiplied by y1 of t, no, minus 8.5, plus 9.5 multiplied by y2 of t, plus 2.5 multiplied by y3 of t, minus 5.5 multiplied by y4 of t. And the derivative of y2 of t, which is the second coordinate function of our solution y, well, that derivative is governed by both the value of y1 and y2 and y3 and y4, and is given by minus 3 times y1 of t. So what I'm doing here is I'm taking this matrix here, and I'm multiplying it with y, and plus, no, not plus, minus. So I'm taking the second row here. The second row gives me the coefficients for the for y prime 2 of t. So minus 5.5 times y2 of t plus 7 times y3 of t minus 0.5 times y4 of t, and so on and so on. Now, what does this mean? Well, this means that if I want to find y1 and y2 and y3 and y4, then I will need to use all the information I have about not just y prime of the first coordinate function, like if I want to find y1, then it's not enough to just use the first equation. I actually have to use all 4 differential equations, because y1 is part of the expression in all 4 differential equations here. And compared to the earlier one-dimensional cases, this also means that when I have found my solution y of t, well, if I'm asked to plot y of t, then it's not just a question of plotting one graph anymore. I'm actually plotting the graph of 4 coordinate functions. So I will have y1 of t, and then maybe I will need to plot y2 of t, and y3 of t, and y4 of t. So this is just something that I'm doing right now, just so that everyone knows that when I'm talking about this system of linear first-order ordinary differential equations, I'm not just talking about one equation. I'm talking about 4 equations, and I'm not just talking about one-dimensional function as a solution. I'm actually talking about the solution that has 4 coordinate functions. Now, how do I solve this using a numerical method? Well, using the finite difference methods that we have already been introduced to, we may actually solve this equation quite easily. So which ones do we know at this point in time? Well, we know the forward Euler. We know the backward Euler. And we know the trapezoidal method. And up till now, we've only used them in one dimension, where the difference formulas were given in table 1.3 on page 16. So for forward Euler, we said our best guess for the next value of y is just the present value plus step size k multiplied by our approximation of y prime in this time point. And with the backward Euler, we approximated y prime by using the value from the next time point, so fj plus 1. And then the Trapetz method, we approximate the derivative as an average of fj plus 1 and fj. So if we were to translate this into matrix language, well, it's not that hard. We just turn everything into matrices and vectors. So instead of just one number, yj plus 1, we now have yj plus 1 as a vector, which looks something like this. Well, y1 j plus 1, y2 j plus 1, y3 j plus 1, y4 j plus 1. And that is equal to the vector yj. And we start this off in y0 as given in the exercise. So y0 is this. So our first value for j equals 0 is y0 given by this thing up here. And then we can add to it the step size k, which, well, is that a matrix? No, because that's just still a number. So we can add to that the step size k multiplied by the approximation of y prime in the time point tj, which for us is just given by the matrix A multiplied by yj. Well, isn't that pretty? So when we start in j equal to 0, well, we know this matrix, and we also know y0, and we also know y0 here. So we can find y1 as a four-dimensional vector by just plugging all the known values in here. So that's the forward Euler method when we solve systems of differential equations. Now you have to be a bit careful with how you save these y1, y2, y3, y4, y5 vectors, because they are vectors. So instead of saving your results inside an array that's a vector, then you will probably have to save your results inside a matrix now. But think a little bit about that. Make a drawing or two, and you'll probably figure it out on your own. And with the backward Euler, we just use exactly the same approach, but where we now realize that instead of using yj here, we use yj plus 1. Now, as we noted in week 1, the backward Euler is an implicit method, and as we also did in week 1, we actually isolated yj plus 1 in this expression here. And that is also what we need to do in this expression. So remember your pluses and minuses and how you do matrix multiplication when you do this. And remember that matrix multiplication is not commutative, so for two matrices, A times B is not the same as B times A. That's important. And so you isolate yj plus 1, and that will be equal to something. And then you just go forth as you did here. And the same with the Trapetz method. Then you just have yj plus 1 equals yj plus k squared times a yj plus 1 plus a yj plus 2. No, plus a yj. like that. And also the Trapetz method, what's that? Well, the Trapetz method is also implicit. So here you'll also have to isolate yj plus 1. And also remember that matrix multiplication is not commutative. And after you've done that, then you're ready to go and you're ready to implement the finite difference methods that we have learned in chapter 1 on a system of first order ordinary differential equations.